Hey guys, thanks for tuning in. I wanted to make a little video about the relationship between polar coordinates, which we've learned recently are defined with a radius and an angle, and how we can transform them to Cartesian coordinates, which is represented with an x and a y. We have more experience with this. We're relatively new with polar, but sometimes it's more beneficial to have an equation or an expression or a point in one form as opposed to another. So here we go. How do we transform back and forth between the two? We give a quick little background using the unit circle, using SOHCAHTOA, and using this sketch down here. If you pick any point in the coordinate plane, it would be represented with an x and a y, meaning that you've gone over x units and you've gone up y units. And if you change the quadrant, you could change the sign, making it negative or something. But more recently with polar graphs, we've also represented these points as basically an angle, which we're calling theta. And then, depending on circles, how far it is from the pole, the middle, that origin piece. And so this point that I have right here can be represented with an x and a y or an r and a theta. And this is where we're going to get our definition. So check this out real quick. Using SOHCAHTOA, I could say that sine is equal to the opposite over hypotenuse. And I could also say that cosine is equal to the adjacent over hypotenuse. And if I multiply everything by r, I could say that r is equal to, y is equal to r sine theta. And I could say that x is equal to r cosine theta. Again, all I did, guys, is multiply both sides by r. Crosses those out. And then last thing, if I do the Pythagorean theorem, I could say that this leg squared plus this leg squared is equal to the hypotenuse squared. So what I'm trying to do is I'm trying to set the stage and create a way that I can convert x's and y's to r's and thetas, or r's and thetas to x's and y's by going back and forth. And so these three things that I boxed down here are going to be kind of our transformations, our equations that allow us to turn in, again, Cartesian to polar and polar to Cartesian. So I'd like to do a couple examples. Here's how the questions are going to kind of be phrased. We have an r equals 2 sine theta, and we want to transform it into Cartesian. And what that means is our goal needs to have x's and y's. That's what it means to be Cartesian. And what we have to work with is these three definitions. We have that x is r cosine theta. This is your cheat sheet for today. Y is r sine theta. And x squared plus y squared is r squared. These are your go-tos. All right, so here we go. There's a few strategies that we'll talk about, and then a few that I'll let you try on your own. But it'd be really nice if I could somehow get, r sine theta to show up, r squared to show up, because when you get these things that are underlined in purple to show up, you can transform them into the goal. So it takes a little bit of practice, but I'm going to start by multiplying both sides by r. Why I'm doing that might not be quite clear yet. What I end up having is 2 r sine theta. Remember, when you do a product, you can move it to any order you want. And now if you take a look, I've got some options. R squared, substitution, is x squared plus y squared. And r sine theta, is y. And guess what? I'm done. I've got rid of all my r's and thetas, and I've turned them into x's and y's. Now, you can leave it like this. Sometimes what we do is we can move everything to one side. But this is the answer. And it's a Cartesian equation for a circle. And that might be familiar to you, or maybe not. I'm going to do a quick little review page with this. But the idea here is, if you did have the time and the energy to graph this on a polar graph, or to graph this on a Cartesian graph, you would get the exact same graph. And I'm going to show you that to kind of end this lesson in a few minutes. All right, so how do I know it's a circle? How do you know what shape it is? You could graph it, but maybe you don't want to graph it because you don't have the time. So here's a little cheat sheet, and I'm going to go through it quickly, and if you want to pause it and write it down or take a screen capture or something, more power to you. But if you have a bunch of terms with squares and not squares, and A, C, D, E, F, those just represent numbers, coefficients. Here's how you can determine if, you have a circle, an ellipse, a hyperbola, or a parabola. If x squared and y squared have equal coefficients, so the number in front, whether it's 1, whether it's 4, if they have the same number in front, it's going to be a circle. That's how I knew this was a circle, because they were the same. Ellipse. If you have unequal coefficients but the same sign, so maybe I have a 2 and a 1, that would be an ellipse. Maybe I have a 2 and a 5, that would be an ellipse. They do have to both be positive, or they have to both be negative. Anytime they're different, you have an ellipse. All right, hyperbola. If you have an x squared and a y squared and they have opposite signs, one positive and one negative. So you must have, this would be an ellipse. Hyperbola. Can't speak. If you had different coefficients, that would be a hyperbola because you have one positive, one minus. Now if you did this, boop, that'd be an ellipse now because they're the same sign. But anytime you have different coefficients, it's going to be a hyperbola. And then parabola is if you only have one squared term. So if you have, an x squared plus a y minus 6x, I only have one squared term. If you had something like this, x plus y squared minus 7x plus 9, who cares? The idea is I only have one squared term. That would be a parabola. All right. Last example. I like to keep these videos short. Transform this polar graph, because it has r's and theta, to Cartesian coordinates. So again, I want x's and y's. So here we go. First thing I'm going to do is I'm going to, cross multiply. And what I'm going to do is essentially multiply by the denominator, because I like to get rid of fractions. So up here, whether you don't quite see it yet, is I'm multiplying the right side and the left side by the denominator in hopes to cross that out. All right, now I'm going to distribute in. So I have 2r minus r cosine theta. Now I'm doing this out of experience, but I'm also doing it because r cosine theta, which just showed up, is x. So I'm trying to chip away and turn these r's and thetas into x's. So I'm getting closer. All right, now I just need to somehow get rid of this guy. And one strategy we're going to use is to isolate the r. So again, see if you can follow my math. I just added x to both sides. And one way to get rid of r is if I can make an r squared. So I'm almost done, folks. What I'm going to do is, I like these colors, I'm going to square both sides. Again, I'm thinking ahead to make this substitution. I hope you see it. You can pause it, you can try it, or you can just watch it as we go. But I have to square the right side also. Got to keep those equal. So again, going back to, Math 2, FOIL method, box method, you got 9 plus 3x plus 3x plus x squared. FOIL method, all that good stuff. So the right side, I've got this. But r squared is x squared plus y squared. So I keep checking the time because YouTube cuts me off at 15 minutes. Keeps my lessons short. So if I basically combine some like terms, I'm essentially done. But a lot of times what happens is the final answer, everything will get moved, to one side. So I've got 3x squared plus 4y squared minus 6x minus 9 equals 0. So, move everything over. So I got this answer. So just to kind of recap today, this is pop quiz. Is it a circle? Is it an ellipse? Is it hyperbola? Is it a parabola? Well, they're both squared terms, but they're different, and they're both positive. So this is an ellipse. Again, they're both positive, but they're different numbers. So it's an ellipse. And what I want to do is I want to just show you very quickly these two graphs. So short-term memory, think of that graph, the original, and think of this graph, the transformation. If you, here's the graph of the polar graph. It's a red ellipse. Think of an ellipse as like a stretched out circle. It's a fancy name for an oval. And then the second one, watch it closely. This is my answer in Cartesian. Look at that. It's the same graph. When we graph it, it's right on top of itself, which means I did it right. So, kind of fun, guys. Thanks for tuning in. Try converting these polars to Cartesians. Good luck. Thanks for watching.